This is the libhal biweekly meeting. Today is December 30th, 2025. Let's get started. All right, for the agenda today, I'm just going to be talking about async context. I spent a lot of time thinking over async context, improvements to it, and a variety of things. Today, I'm going to spend a bit of time just trying to explain again some of the rationale for async context. But also, I want to kind of go over some of the fundamental aspects of coroutines that might not be very obvious. A lot of the stuff sounds very hand wavy, but there's like something deep down to this. All right, so the problem we're solving. We want to be able to use C++20's ability to use structured concurrency. And by that I mean co-await. The co-await keyword, as well as co-yield and the other ones, is a very powerful thing that we get to have in C++. It's basically a way to tell a function, or to tell the compiler, hey, this is a point in a particular function's code that is a suspension point, or potentially a suspension point. A lot of the things that can happen with the co-await expression. C++20 provides coroutine support, but coroutines by default dynamically allocate their memory. We're going to go into some examples that kind of show why that is. But before we get into that, we need to make sure it's clear that embedded systems will not accept anything that uses dynamic memory allocation after initialization. Some say none at all. I think that's kind of ridiculous, although I don't think what we're building gets in the way of that, although maybe some people might argue use of polymorphic allocators, even though the memory is statically made, might be a problem, whatever. But in general, so long as there's no additional new memory being allocated, specified after initialization, people are usually fine. The only thing that's allowed is, and here's a bit of an observation from me, I find that the only thing that's actually allowed for embedded systems in terms of runtime dynamic memory allocation is if it's from the CPU and it's calling a function. Because anytime you need memory to call a function, you need to allocate some memory on the stack. You move the stack pointer down, and then you access that memory. This could be a problem, because eventually you'll reach the end of memory if you keep going down that route, and then eventually you will either interact with memory in the heap, memory from data, BSS, other sections of the program, or you might hit the end of RAM. These are things that I've observed and done in the past before. You need to have some precautions to make sure that doesn't happen. There is one key benefit of a stack, though, is that it's packed. Unlike a heap, where you can have segmentation, you can have little gaps here and there, stacks are not capable of doing that. So putting that all together, the requirements for an embedded async library for using C++20 and for libhal would require deterministic memory usage, explicit control over scheduling, and we have to figure out and make sure there's a way to integrate a real-time operating system, a normal operating system, or whatever the user wants for their bare metal system. And I think what we have does all those things. Before we get into that, let's talk about how coroutines work normally. So I have this coroutine over here. It returns back a standard task. This is me making some assumptions about how task is implemented. I've read it before, but I've forgotten it. It's been a while. Anyway, let's say that we have a vector that's it's in this vector that's a local variable of this function, of this coroutine. We have some for loop. This one, I meant to put in a length of some sort here. This doesn't make any sense. But the idea is that we're going to keep pushing back information on here. So I kind of messed up this example, but just take my word for it. We're pushing back onto this, into this thing. And then we have a couple other operations that we're going to do. Every time we see a co-wait expression, it means that this particular function can suspend at this particular point. In general, this is a handoff from this coroutine into the next coroutine, just like you would see with a function call, where you would make one function call and then control over the CPU is then given to the next function call, which then does its thing. whenever you hit a suspension point, let's say this actually does suspend, then whatever part of the code called resume, and I haven't really said this yet, but this task object should have a resume function as a part of it. So once you get that, once you call your coroutine function to get back a task, generally your coroutines don't start automatically. They start paused, and then you can start them. So you call this function to get your task back, then you can call resume to start it. When this hits a call wait, that function comes back. That's when you return. That's when resume returns, is once the coroutine reaches a call wait statement. The coroutine can be resumed from where it was suspended. So if it was suspended at this point and you hit resume again, you call resume at some point in your code, it will pop back over, check the for loop, go back in here, do call wait again, and so on and so forth until this is finished. And again, this is mistaken. This is not. This is broken code. I don't know how I wrote it this way. One thing to keep in mind is that this vector, there are multiple points in which this thing suspends. This loop here and then these two spots here. It must live. This vector must live as long as the coroutine frame itself. Once this thing finishes, then this thing can be cleaned up and destroyed. But until then, it cannot be. So coroutines are interesting because they actually have, in my opinion, two stack frames. They have the temporary call stack frame. So when you resume this thing, if whatever between this point and this point, if it has any more memory, that will become part of its stack. But the parts that go beyond suspension points, those must go into the coroutine frame itself, and those must persist as long as the coroutine does. So the call stack temporary frame only exists as long as the function is currently running, and then the persistent has to exist for the entire lifetime of this coroutine until eventually you return out, which is just hitting the end of the function. I know that's a lot. There's a lot of information I'm going to be throwing out at you guys, so just keep this. So take it slow. Maybe rewatch this video later on to get a better idea. But that's pretty much the basics of like what these parts of the coroutine do. One thing I want to talk about also is what a coroutine frame would entail. We're not going to go into all the bits. Like I'm not going to tell you what a promise type is. It's not important right now. But the coroutine frame, in order to know where it was and where it's going, it needs to remember something about where the code was. Naively, you could use a program counter. Another option is use an offset. You could have an index number with a switch case so that you just jump through the switches. There's like options for what this can be. Not important for us. The compiler handles this for us. The promise type is really just a way to remember things. It's not super important for what we're talking about now, but that gets put into the coroutine frame as well. Any parameters, we didn't take any yet, but if we had any parameters, they would be copied into the coroutine frame as well, so we have access to them. And then finally, any local variables that cross suspension points will also need to be part of the coroutine frame. So just to kind of recap, automatic storage, which just means variables that are on a like function frame. Basically, when they get once you leave the function, they get destroyed. Those cannot persist beyond a return call. Those cannot work for this. Static storage also couldn't work for coroutines because just like a function, you can call a single function in multiple threads, potentially even multiple times if you're doing recursion. Not that you should ever really use recursion anywhere, but like that's an example of where you'd have duplicates of the same frame. Because of that, there's not going to be a single sentinel my coroutine memory. Otherwise, we can only call it in one thread at a time. So static storage doesn't really work here. We can't have one per one of these things. The only option you really are given is some sort of dynamic memory, where the dynamic memory starts at the scope creation of this thing and then ends at the end of the curly brace of this thing. So to kind of illustrate this yet again, kind of how they work, let's kind of look at this example here. We have main, it calls coroutine A, which allocates on the heap, gets back a task, we check to see if it's done, and if it's not, we resume it. Okay, so we go in here, we're gonna wait for 25 milliseconds to represent waiting for some duration of time. I didn't put any variables in here, but you imagine there should be some. Then we call cowait B to do some operation with coroutine B. Waits 50 milliseconds because it's doing some work, calls coroutine C, that does some work for 100 milliseconds, comes back, and then we wait for 50 more milliseconds, do more work, then we return, go back up to here, 25 milliseconds, go back. Just typical function flow. But when this happens, when you first call task equals corout A, this is your heap beforehand. There's some memory used here, some memory used up here. We'll allocate some memory in this spot here. This is a very small heap in this case. Once you resume it, it'll begin executing, and then it'll reach corout B. It'll allocate the memory for corout B. Corout B will remember who called it. So it'll go, oh yeah, corout B was called by corout A. I'm going to keep an address to that. This is called a continuation, which is basically just a return address like you'd have with normal functions. So you'd resume. That would go to corout B. You would then go into corout B, resume again. This is like the fourth resume. You call this, do whatever happens there, then call corout C. Can't fit the memory here, so you got to go a little over past this point and then allocate your memory here. And then corout C will have a return address to B. This is really just saying is when corout C ends, it knows how to get back to resuming corout B. And then when that ends, it goes, oh, well, resume corout A for me, and then so on and so forth. The way that I design our coroutines, and I believe almost everyone should do it this way, once one of these functions ends, it continues off directly where it was before. There's multiple benefits for this. One's performance, one's for stack frame stuff. I'm not gonna get into it, never mind. But basically, this is the nature of how the allocations would occur. To drive this home, I have another example. Let's say that we have two tasks that we're working with, one called mycoroutine1 and another one called mycoroutine2. Anytime we call resume on this, you'll have your temporary call stack that goes on your actual stack, the one that your CPU uses, and you will have access to your coroutine frame that's on the heap. If you return from that function and then call another resume function, well, the previous coroutine frame gets removed. Then the new mycoroutine2 frame gets put on and gets used there. The thing I like about this is that your stack usage is basically limited, like your CPU stack usage is limited to whatever you're calling at the time. So your memory gets pulled up in your heap and gets pulled up somewhere else, but the stack usage, the temporary variables, those only go down so far, which actually has some pretty cool implications for embedded program or for real-time operating systems that pre-allocate their stacks. You can make them small, potentially, so long as you don't use up that much memory in here. So there's some cool benefits that can come from this. If my coroutine does some I/O operation, then it will clean up itself and then put this on the stack. And then same thing with my coroutine2, clean itself up when it returns, then put the next thing on the stack. So there's only really ever one coroutine per thread on a stack at a time. That's pretty much how that goes. Oh, and then if you ever clean up that object, it's finished, then you go back to this. So a couple of observations about coroutines overall. After playing with them, I realized that they allocate frames identically to function frames. The only difference between a coroutine frame and a function frame is that a coroutine frame has to be preserved until it reaches its co-return point. A little more meaning to this, the stack frame must live, I don't know how I was supposed to spell this. The stack frame must live off the stack. So that's what I meant. The coroutine frame must live off the CPU stack. That's what I was trying to write there, and it meant to say. The idea here is things on the stack are temporary, and if you want to make them live forever, you either put them in their own thread so they have their own stack, their own CPU stack, or you put them somewhere else, and that was the choice that C++ committee made, was to heap allocate them. But then I thought, why not provide a fixed size stack that coroutines can allocate and deallocate their frames on? For the requirements for an embedded async library, this would fix one of the deterministic memory usage parts. We would only allocate once for the whole stack frame, or never really once. We could just provide memory for it. So Let's kind of go over the core concepts of async context. This is our solution to this whole thing. There's the scheduler, which is a notification sync for state changes. So anytime a coroutine changes its state, the scheduler is notified of it. The scheduler also provides memory for stacks. There's also the context. This manages the coroutine chain and transmits state information to the scheduler, or state transitions. And then finally, we have the future, which is the handle that you use in order to interact with the coroutine. You can resume it, you can destroy it, you can get how much memory it's using up, you can get a whole bunch of things from it. You can access the context from the future. So the future is connected to its context, and the context has whatever the latest coroutine is for the future, which we'll go into more details later on. And then a task is basically just a future void, which you can also just write future void if you want. The scheduler. These have virtual APIs that do the same thing. So the do underscore and the do underscore, I gotta change the name with this to do stack memory allocator. But anyway, the scheduler is called by a coroutine. The coroutines have the ability to actually invoke, say, hey, I want you to say that I'm blocked by input output, and then pass that to context, which then passes it to its scheduler that's assigned to. When you schedule something, you schedule which context is needing to be scheduled, what its block by state is, and what its block information is. We'll go into what the block by states are in a bit, but the idea is that there's different states that you can be in that tell you whether or not you're blocked. There's also one state called blocked by nothing, meaning that you're ready to go. For the block information, let's say you're being blocked by time. Well, we can actually give you a time duration to stay asleep for. Or if you're being blocked by synchronization, we can give you which context you're currently being blocked by, which can be used for priority inheritance type things. And then finally, we have an API for getting a stack memory allocator. This API will only really be called at the creation of contexts and shouldn't be used any other time. It's a bit of a dangerous API to have around because you could just allocate randomly, but there's ways to get around that. So let's talk about the 5 blocking states. So you can be blocked by nothing, which means that you're ready to run. That is also a state transition you'll get, saying that this thing is not blocked by anything yet or anymore. You can be blocked by time. So if you saw those co-wait 50 millisecond type things, I've added that into async context. It basically says, scheduler, please reschedule me after this amount of time. We also have blocked by I/O. This is over DMA or something else that's occurring, what have you. But the idea is that the CPU no longer has to do anything more to allow this particular transaction to occur. So we're going to notify the scheduler that we are currently blocked by I/O, and the scheduler can do something smart about that. One thing about this is that if you do say that you're blocked by I/O, it is required that some part of the system wake that particular thing up if it's an appropriate time to be woken up. For example, if you do an I2C transaction and it completes, and there's an interrupt for that, that interrupt should unblock your coroutine, and that'll tell the scheduler, hey, make sure to set this as being unblocked, or at least know about it and do something about it. Maybe put that context somewhere where it's useful. Sync. This means that there is a contention between 2 coroutines that want a particular resource. So one of them is going to be blocked by synchronization, and the other one's probably going to get access to it and get blocked by I/O. That's why we pass in the context pointer here. The reason why is that if you're blocked by sync, you may also want to know who you're blocked by. So then if that thing becomes unblocked, you can then reschedule the other blocked by sync contexts. And then finally, we have blocked by external, which basically means that we called out to some other API, some other coroutine type thing. And the way that coroutines work in C++ is that coroutines in a way tell how to schedule themselves. So they have to manage scheduling themselves. If we call out to something that's outside of async context, we don't know how they're being scheduled, so we have to wait for them to finish up however they're doing things, and then once they call us back, then we can go back into our groove. So here's a very simple example of what using async context will look like into the future. Not all of this is complete, and we don't even have the polling scheduler. Like, that's just a made up thing that I came up with. But yeah, polling scheduler, give it a pool of memory. You call async context, you pass in your scheduler, and you pass up how much memory you want for that stack. We can make 2 of these. We can now pass the context to coroutine functions, which will return back a future, and then pass that into the add function of our scheduler. That'll add it to being scheduled by the scheduler. We can do that with another async function, and then scheduler will have a function called resume, but also have a function called poll. These are actually options. These are not things that are required by async context, but I would recommend that whoever builds these up would supply a poll and a resume function. And what it'll do is it'll concurrently run between these 2 coroutines until they finish. If they finish, you unblock and you leave the spot. But yeah, this is what I expect the code to look like. You do these for a couple lines at the beginning, and then you can pretty much do the rest here. If you don't want to, let's say, if you want to call these and manage them directly, you can actually get back a task object from any one of your async functions, and then you can resume them. One little keynote, you can't reuse a context twice until it's finished. I don't have a way in software to detect if you've done that. It's kind of hard to do that without making an asymmetric build and design, and I'm not sure if I really want that anyway. You can get back a task, get back a future, and then from there you can resume that future. You can also sync weight that future. Sync weight that future, which basically will block until that future is complete, and it'll get back a value of some sort. Deep down, poll is just running resume on both tasks or both futures back and forth over and over again. That's kind of the idea of a very basic polling scheduler. That should be able to do that. And now finally, context, which is what this entire library is named after. This manages the coroutine chain and transmits any state transition information to the scheduler. What the context does is that each one owns its own fixed size stack buffer. When you create one of these contexts, using these examples here, you pass in the scheduler, and that's when it takes this number here and uses it to allocate its stack frame. And then it saves that number in order to know how big the stack frame was in total, so it knows its capacity. The coroutines allocate their frames from this stack. And I'll show you some examples what that looks like a little bit. But basically, rather than allocating directly on the heap wherever there's memory, we do it in an ordered fashion with our own context stack. Memory is provided by the scheduler stack memory allocator, and this is memory safe allocation. So if you do exceed the coroutine stack by doing something recursive or just making too many calls that eventually overloads the stack, it'll throw an exception called bad coroutine alloc. This will not propagate through the coroutine. It'll actually propagate out to the scheduler, which is actually on purpose, because it needs to know that something went wrong in the resumption that was outside of normal behavior, and then it could do something about it, which is usually just to destroy it afterwards. So let's go over what this would look like when you have this little stack. Now, because this is our own little allocated memory just meant for coroutine stacks, it can be nice and ordered. So let's say that we've called some coroutine called A that gets loaded onto the stack, and it's currently the active coroutine, meaning that it's the one that we're currently running. So this is loaded onto the context, and then at some point we resume, it executes, does its thing, and then it reaches a co-wait statement, and it co-waits B. So we do co-wait B. Now B is the active coroutine. Then we're going to suspend, give control back, and then you can do whatever else you want. Then when you resume that context or that future again, it might run up until it hits a co-wait C. Now C becomes the active coroutine with a little continuation to B, and then B has a continuation to A, and then control is given back to you. And I just want to make sure that's kind of clear here. I don't know if I said that enough before, but if you run this bit of code here, it basically runs up until it reaches a co-wait statement, like we've shown in this example here. You run up to the point where you hit a co-wait, like this one here in this particular example, and then you will suspend, and this will return back. Then we can loop again, and then call resume again. So just wanted to make sure that was clear. Now, from here, we are on C. We then resume it one more time. C finishes, it returns control back to B, and then also deallocates this memory off the stack. This will happen back and forth like you'd expect a typical function to behave. And that's pretty much how the allocation scheme for async context works. The other cool benefit of this is that you have no overhead that you'd expect to get from the accessing heap, accessing dynamic memory, calling malloc. That's not going to happen here. It's always going to be bounded within this. So there's some cache locality benefits. There is the fact that the allocation is very fast. It's just push the pointer back, save it, and then there's one other place we have to save it into, but that's not super important. Oh, and then also checking to make sure we haven't hit the end. So it's a little more expensive, but you know. And now for the fun part. This is the part that I've spent the last week and a half grinding mentally about. I was talking to Milo about USB stuff. Actually, not even USB stuff, just I2C related things. And we were dealing with a device that seems to, we need to check, but seems to clock stretch. An I2C device that clock stretches, which if you clock stretch, a lot of devices will just simply get halted. Their I2C bus will be stuck until it's finished. And if you are in code that's waiting for that to finish, your code is now, your system's now halted for the most part. So I was like, well, this is exciting. With a scheduler and with the context system, we can detect when a context hasn't been used for a long time. We can have a watchdog that goes, hey, this particular context hasn't become unblocked in this duration of time, or nothing's been unblocked in this duration of time. We can do something about it. But I realized that that's external. Like, what are the things that you can do externally to a coroutine? Just from my experience doing this, I can technically inject an exception into the coroutine pipeline and have it passed up. I spent like 3 days making sure that would work and found out that actually that would not work. It has nothing to do with exceptions at all. Simply trying to use error propagation to signal a timeout is actually flawed in this whole mechanism. It's just not the right channel for it. That's a longer discussion for another time. Maybe when I do a full talk on async context, I'll go into that more detail. But basically, what we realized was, or what I realized was, if we are stuck, we have some asynchronous I/O that happens with I2C, and even though we're able to detect it, let me finish one part about the whole story I was talking about before. Things that you can do from the outside. You could call some code, you can log it, or you can destroy the coroutine, so long as you know that it's not currently active, so long as you know it's suspended. But that's not really helpful. I would hope that we would have some way to allow D or some code to be able to have a timeout of some sort. So let me go over the scenario here. Let's say that D wants to see if E will take longer than 1 second to complete. Let's say this is our I2C communication and we allow it to go for a whole second, which is absurd, but let's assume. D doesn't have control over the context and cannot run again. So if we call E with any information, we're pretty much just stuck. E can run as much as it likes. It has no idea that it's being supervised in any way. Technically, if we remembered this particular the coroutine where this coroutine is located, we could resume it. You can resume pretty much any one of these, but you don't want to, because what happens is D resumes as if E had completed, and then you have undefined memory, and that's basically UB. So that's dangerous. What we need is a way for this D here, to stay in control, stay as the active coroutine, but somehow still execute E. Or in other words, you have some driver code that wants to make an I2C transaction happen, communicate over I2C, but wants to make sure that I2C operation doesn't doesn't stall forever. So you need to still be able to be resumed so that you can actually observe what's happening in this other context. What D needs is another context to run E on. And that is what I spent the last 3 weeks, 1.5 weeks thinking about. Introducing proxy contexts. All right. A proxy context is a context that borrows the remaining stack memory from the original context. So it actually literally shrinks the previous stack memory from being the whole thing with some unused spot into just the amount that was currently there. This is a way to prevent you from using this again. It has its own separate active coroutine handle. And actually, there's a mistake here. I need to put a play button at this spot because technically this one can be resumed as well. So it has a separate coroutine handle from the original. Any state transition changes that happen with the proxy get transmitted all the way over to the original. And the reason why this happens is that the scheduler only knows about the original coroutine, the original context, and doesn't know anything about proxies, so we can reschedule our original context by shoveling anything that we see up to it. Any coroutine that has a proxy coroutine or proxy context on it becomes what I call an inline supervising coroutine, or just simply a supervising coroutine, or even simpler, a supervisor. It uses a proxy, and that proxy is on the coroutine stack. That proxy is used to launch an async operation like E, but keeps itself as the active coroutine on its own context. The cool thing about this is that it's scalable. You could actually have proxies on proxies on proxies if you wanted to. Let's say you have some bigger task that needs to make sure that every 2 seconds that the system continues to make progress, or that an operation should complete. So it starts its operations. Then here we make another proxy. We have to do some other thing that's going to need to make sure that the operation doesn't take longer than 100 milliseconds. And that does its thing. We have another smaller operation that shouldn't take any longer than 10 milliseconds, and that one's running. So in this case, we can actually nest these backwards. They all have the same size. They're all the same object. The contexts are all the same. They're just different forms of the same object. You can only really make a origin context and then from there create a proxy. So there's like a directionality here. You can't make a proxy by default. And you can see how all of the proxy stacks have been split up to kind of account for the fact that we're borrowing the memory from the previous context. One other cool property that I made sure this had was that whenever you resume this context or its future, it jumps into C. When you resume C, it then performs whatever checks it needs to perform. Then it executes, goes, okay, that's all good. Let's resume my coroutine. So then it'll resume its coroutine, which will jump it into F. F will perform whatever checks it needs to perform. It will then go, okay, let's resume H, resumes H. H says everything's good, resumes F. F does its thing, does whatever it needs to do, and then it calls back, and back. If there was a timeout that occurred on any one of these, let's say you have some interrupt that occurs after a certain duration of time to tell you that something is taking too long. It'll unblock the original context, basically unblocking everyone here. And then this will re-enter from here, go to here, realize that F is the one that has timed out. From there, it can then destroy all of the operations here and then pivot to some other strategy after it's determined that there's been a timeout. And yeah, that's pretty much the idea. So with the proxies, we now have a way to check on our operations. You can only do one. I have an idea of how to do n many in the future, but I'm still not sure if that is even useful yet. But for now, we have a way to kind of break the typical operations of our code. Whereas normally with normal functions, the function at the bottom of the stack, or running on the bottom of the stack, is the current function. You normally can't have functions in between do stuff. There's actual ways you can kind of do that, but I think you know what I mean. This allows us to have checkpoints and have checkpoints that can supervise operations below them. And the memory is just memory that's on the stack of these coroutines, meaning that there's no additional dynamic memory allocation. It's all well bounded and scales for as many as you need. The last thing I will say to all of this is, even though I'm really happy that we have this, we should try to avoid this as much as possible, because every time we have to jump and skip is performance loss to resuming the underlying IO operation. My hope is that you should only really have no more than 2 proxies at a time running. One for your overall task to make sure to manage things, and then another one for any IO that the code knows shouldn't take longer than a certain duration of time, and if it does, then it has an expectation of what that means, like talking to an I2C device and it clock stretching on you. And you knowing that, oh, this happens if it's in a weird state, and if it takes longer than this, that means it's probably bugged. I need to do something about it. And that's pretty much it. Things we have not discussed today: how to implement a scheduler. We haven't even talked about like best ways to utilize the information that you can give to a scheduler. If you've ever worked with scheduling or even thought about it a bit, you might have some ideas of how you could utilize the previous block by states to do things. And I have not gone into detail about how to actually put together a timeout. I'm really just showing like pictures of how it can work. I'm still working on the proxy implementation. I have all the pieces together. I just need to actually start testing it out and make sure the tests work. So it's not finished. I need to test it, then I'll know if it's actually doing what I want it to do. And then I'll be able to show you examples, which will hopefully happen in 2 weeks from now. So yeah, that's pretty much it. Thank you guys for coming.